Now, levels of abstraction, like a system can be can be viewed at different levels, as we have already seen that we can see it at gate level, we can see it at transistor level, or it may be even at a much higher level, at a functional level we can see. So, as we go higher and higher levels of implementation, so we have got lesser detail about the internal implementation. So, implementation details are not available. So, as a result, for test generation, so it will be more at the input output situation, input output points only. So, it will not go into the details of the implementations. So, fault models based on gate and physical level. So, when we are considering the gate level, so we have got some fault model. So, when you go to physical level in terms of transistors and wires, we have got a more detailed view of the system. So, as a result, the types of faults that can be detected by a lower level fault model, so that cannot be, that may not be possible with a higher level fault model. But of course, if when you are going for this lower level fault model, the number of faults and number that are possible becomes huge. So, as a result, it may be difficult to generate test patterns for all those faults. So, that way higher level model can help us in generating test patterns which are much more compact in nature. So, as a typical example, so consider two circuits here. So, both of them are corresponding to say this particular Boolean function. So, a b bar c bar plus a b c plus a b c. So, this is a b bar c bar plus a bar b c, this bar should move here, a bar b c plus x a b c. So, this term is do not care. So, now naturally I can have a different type of grouping. So, in one realization it may be like this a b c plus a bar b c bar. In another case, I can have this realization. So, a b plus b c bar. So, that is also possible. Now, you see that when you are looking into this circuit, so this is the circuit implementation, and for circuit B, this is the circuit implementation. Now, if we use a test vector generation for this circuit, okay, so these are the test vectors that can detect different faults on all these lines in the circuit, whereas this type of test vectors, it will not be able to detect these faults. So, the faults that are marked, so this line stuck at 1 or this line stuck at 1 or this line stuck at 1. So, these faults cannot be detected by test vectors that I have generated considering the second implementation of the circuit. So, if we have so implementation dependent test generation, so that is important. So, we have to have the proper implementation details for generating the tests properly. Now, how do we test a system? Okay. So, what are the components that are needed when we are trying to test a chip or a system? So, one very important part in this testing process is the automatic test equipment or ATE. So, this will be coming to us again and again. So, this is some sort of computer. So, that will store the test patterns and responses in it, and there will be some facility by which these test patterns can be applied to the circuit under test through the channels of the ATE, and the responses will be collected, and then you can compare those responses with the fault free responses stored in the computer's memory. So, this ATE, it will consist of a computer for central control and flexible test and measurement for different products. So, depending upon the type of tests that can be done with this ATE, we should have facility for applying those patterns or measure the values, or if it is allowing you to do analog testing, so IDDQ testing. So, you have to be able to measure the current and all that. Second thing is the pin electronics and fixtures. So, how do you apply test patterns to the pins and sample responses? As we know that these chips that we are testing, they can have a different number of pins in them. Similarly, this ATE that I have, so the ATE also will have a number of channels. Okay. So, this ATE channel width is also has to be some fixed value. Now, the problem is that suppose we have an ATE which can have which has got a channel width of say 40 bits. Now, I have a chip that has got say 100 pins in it. Now, how do I test this 100 pin chip with a 40 an ATE with the channel width of 40 bits. So, naturally we have to do some sort of multiplexing. So, how can we do all these things? So, that is actually a part of the ATE. So, ATE can tell like, okay, you can apply test patterns in this fashion by doing the multiplexing. So, this is spin electronics and fixture. So, this will be talking about what are the ATE channels we have and how to use them for applying test patterns. And the third thing is the test program. So, that will control the timing of test pattern, compare responses to known good responses. So, this when the test patterns are to be applied, in what sequence, and it will collect the response at what time it should be collected, and then the comparison part. So, these are actually part of ATE, and since the circuit complexities are going up, so this ATE will ATE will need to have large amount of memory to hold the test patterns and the responses. So, that way the cost of the ATE is also becoming enormous. So, if it is it depends on two factors, the channels, the channel width, and also the memory capacity that it has. So, there are challenges like as IC technology is increasing significantly. So, chips are becoming more and more complex, but ATE that is that is some most of the company, the fabrication house or the testing company, they will be having one ATE or say some certain capacity. So, it is not advisable that with every new chip that we design, so we have to have an ATE that can run at a higher speed. So, every new version of chip running at higher speed, the ATE speed should also go up. So, there must be some technique by which we can use these older ATEs for the faster chips as well. So, that is also a part of this ATE design. So, ATE stores the test patterns. Now, where from do we get those test patterns? Okay. So, they are actually coming from some automatic test pattern generation technique called ATPG. So, there are very nice algorithms by which we can generate test vectors for a given circuit on specific fault model. So, we say that okay, so this circuit has got say 10 points at which there may be faults. So, each of those is, if we are considering say stacked fault, then for every point we need to generate the test patterns. So, there are certain algorithms by which we can do this test pattern generation. So, they are known as automatic test pattern generation algorithms. Second important another piece of software. So, ATPG is a piece of software which is generating the test patterns. Another important piece of software that are needed by testing community is the fault simulation techniques. So, what happens is that I am given a set of test patterns. Now, how do I know how many of the faults are actually covered by this test pattern set? So, for that purpose I need to inject those faults into the circuit, apply the test pattern set and see whether it is detecting the faults or not. Now, naturally we cannot do this before the circuit comes into existence. So, and particularly the physically that fault has occurred in the circuit. So, but that way we cannot wait for the faults to occur. So, what is done in software itself? So, we can have a piece of simulator which will be injecting those faults into the circuit description, and it will try to see like what is simulate the circuit in the presence of those faults by applying the test vectors and see whether it is giving us the some response which is different from the fault free responses. So, if it is so, then we can say that okay, this test pattern is detecting has the capability to detect the fault. So, this fault simulation technique, so they emulate fault models in the circuit and applies test vectors and determine the fault coverage. So, naturally the question is the simulation time. So, how much time it needs to do the simulation. So, if I have got say 100 test patterns and say 100 faults, and if I am simulating each the system for each fault and each test pattern, that means the entire circuit has to be simulated 100 into 100 times. So, that is a huge number. So, can we reduce this time? Okay. So, there are when we go to fault simulation techniques, so we will see that there are several techniques by which we can do this fault simulation, say parallel simulation, deductive simulation, concurrent simulation. So, there are several techniques by which we can do this over and above the very simple serial simulation. Now, for helping in the testing process, so there are certain techniques that have been incorporated into the design. They are known as design for testability. So, design for testability means, so if a circuit is designed by the designer and the test engineer is asked to do the testing, so it may so happen that it is very difficult to probe certain points inside the circuit, because this is an IC chip. So, I cannot I do not have access to the internal points of the chip. So, I have to do it through the primary input output lines only. So, it may be difficult to access those points from the primary inputs and outputs. So, if it is difficult to access, so it may be difficult to test the faults that might have occurred at those points. So, what this design for testability tells is that we incorporate something extra into our design, so that this testing process is helped. Okay. So, it improves controllability in the sense that I can put any desired point in the circuit to a desired logic value. So, that way it is controllability. Similarly, observability means I have got I can observe the value of some point in the circuit by some technique at the primary output. So, what I essentially mean is that if this is the full circuit that I have, full design that I have now, so it may be that I want, so here I have got the primary inputs to the system, here I have got the primary outputs. Now, if I want to check the status of this particular line, so whether this line is say stuck at 0 or not. So, if I want to test this one, then somehow I have to apply some pattern, so that this line becomes, in a fault free circuit, this line becomes 1. Okay. So, that has to be done. So, somehow I have to apply the test patterns for apply the patterns here, so that it becomes 1. Similarly, if due to this, so this effect of this fault, it should get propagated to some output, so that I can see that this fault has occurred. So, this is so one thing is that to control this point to a desired value, and the second thing is to observe the value at some primary output. Now, if the circuit is quite complex, it may not be very simple to have a to do these things. So, what is done? We have to have some additional hardware incorporated into the system, so that this checking becomes easy. Now, so this DFT, so this is generally incorporated into the design, and the goal is to improve controllability and or observability of internal nodes of the chip, or it may be for PCB also. The PCB also, we have got a number of chips mounted on the PCB. So, that individual chips inputs and outputs may not be traceable. So, we have to have a look at that from the system input output point of view. So, that way we can have we may need to have a PCB also, some feature has to be incorporated, so that it becomes testable. So, there are 3 main approaches for this design for testability assurance. One is the ad hoc techniques. So, second class is a scan design or boundary scan, and the third one is built in self test. So, we will look into each of them in a nutshell. So, ad hoc technique, it means that we add additional internal point, so a test point, so by multiplexers. So, maybe that this point we need to control. Okay. So, this point we need to control. So, what we do? We put a multiplexer before that, and there is a controllability this multiplexer control input is there. So, if this control input is 0, then this normal system data will pass through this, so that the circuit will operate at its normal way. And if we want to if we want to put some particular value at this point, so we have got some test data inputs, and test data input will be set will be passed through this multiplexer at this point. So, this way we can control the value that we have at this point. So, that is known as so controllability is enhanced by this means. On the other hand, the observability. So, if we want to improve the observability, so what happens is that, so this point we want to observe. So, we add another multiplexer and we put it so this is the normal system output can go to primary output. So, we pass it through a multiplexer. So, if this point is selected, then for normal operation of the system, though this normal system data will go to primary output, whereas when we are trying to observe the value of some point, internal point. So, we put it like this. So, what we essentially do is that if this is a big circuit that we have, and we want to say there is one AND gate and this output is going to some OR gate, etc., and we want to control the value at this point. We want to control the value at this point. So, this circuit will be modified like this. So, this AND gate is there. So, it will be passing through a multiplexer, and this multiplexer's output will go to the OR gate. Okay. So, this is this line is equivalent to this line, and there will be another line. So, this is that circuit boundary. There will be another line which will be taking out. So, which we call the test input. So, this is our test input, and this multiplexer has to be controlled. So, in this multiplexer has to be controlled, that is controlled by the test mode. So, this is selecting the test mode, selecting the test mode. So, if this is, if the test mode selects this test input, then the test input can be put into this put at this point, otherwise for normal operation it will go. Similarly, if we want to observe the value at that we have in this point, so it may be difficult because it may be feeding some other gates, etc. So, it is difficult to see the output. So, what we do is that we select one primary output, we select one primary output onto which we want to visualize this point or see this point. So, if this primary output is say finally coming from some gate, so it is coming from say this gate, it is connected to this primary output. So, what we do, we modify it so that there is another multiplexer again. So, the connection established is like this, and this is that test mode. So, in test mode, this line in test mode, so this line value will be available at this primary output. So, that way observability of this point is increased, and similarly controllability of this point is increased by putting this extra components into the system. So, that way we can have this we can add internal test points for controllability and observability enhancement. Of course, it is quite ad hoc, because wherever we feel that it is difficult to observe a line or control a line, we are putting this type of multiplexers. Okay. So, primarily we target hard to test portions of the chip, the part of the chip for which we find that it is very difficult to put a particular signal line to some desired value. So, there we do this thing, and similarly for the output also, where it is very difficult to observe. So, there we actually put this one. So, this is this will be added on case to case basis, and whatever we do from one circuit may not be true for the other circuit. So, it has to be it has to vary from circuit to circuit, and it is hard to test regions of the chip that is targeted in this fashion. Other way out is to have this scan design. So, this is the typical system that we have. So, any system will have this combinational logic and some flip flops in it. So, we transform these flip flops so that they form a shift register. Okay. The basic difficulty that we have is that if I have a combinational logic, so it has got some primary inputs, and there are some flip flops which are the next state flip flops. Now, you see that these being primary input and primary output. So, these lines they can be controlled very easily and also observed very easily, but it is difficult to control say values that I need to put at this point, because starting with the initial state of the finite state machine. So, these flip flops they will have some value depending upon the state transitions that are affected into the system. So, as a result, it is difficult to come up with proper state transitions, so that we have the desired values at these flip flops. So, this scan design is a transformation that will help us in doing these operations. What we do is that say this is the original flip flop that I have. So, this DI is the D input, QI is the Q output and clock. So, it is transformed into something like this, where we put a multiplexer. Okay. So, in this multiplexer we have got this DI coming connected to the 0 line, and QI minus 1, that is the Q output of the previous flip flop in the chain. So, that is connected here, and rest of the thing remains unaltered. So, in a design, what happens is that these flip flops, they form a chain. So, what we are doing is that we have got two flip flops, say for example, in a design. So, we put some multiplexer here, here I have got the combinational logic. So, this data input comes here, whereas from this multiplexer, from this D flip flop, the Q output, it is put here. So, similarly, for this flip flop we have got the input coming from here. So, that will again go to a multiplexer, and this output goes here. So, this way it this output is all these outputs, they also simultaneously go to the circuit for normal operation. So, for normal operation, these multiplexers are selected in such a fashion, so that these combinational logic outputs are fed into the flip flops, so that they operate in the normal mode. But in the test mode, what happens is that this we put some pattern here. Say suppose we put a pattern, a value S here. So, this value S will be coming into the D flip flop, and in the next cycle, so in the next clock, so that S value will go to the next flip flop, and whatever new value we put in this line, so that will come to this flip flop. So, this way it will form a chain of flip flops. Now, once we have got a chain of flip flops, that is forming some sort of shift register for these patterns, for these out of these flip flops that we have in the circuit. So, that they are converted into a shift register. So, for applying test vectors, the primary input part we apply directly. For the this state register, for the state bits, so we have configured these state flip flops into a shift register. So, we shift these test vectors into this shift register. Then the circuit is made to operate in the normal mode. So, when it operates in the normal mode, so this pattern is applied to the circuit, and then the responses are collected again into these flip flops. Now, you see that so when this circuit is operating, when this circuit is operating in the test mode, so what we can do, we can take out this point and say that is our scan out point SO, and this point is scan in, it is SI. So, what we can do, we can scan in the test vector. Similarly, once the response has been captured into these flip flops, so we can scan out the responses through this SO line serially. So, this scan in and scan out operations can be used for putting the test vectors into these flip flops, so that my test application process becomes simpler. And of course, there can be overlaps, like when we are shifting out the response of previous vector, so we can shift in the next test vector. So, this is one of the very standard designs, like with the flip flops that we have in the circuit. So, they are converted into scan flip flops, and they are connected over a shift register organization, and whatever value we want to have in those flip flops, we can shift them serially into those flip flops, and accordingly we can apply some desired test pattern there. So, the CAD tools that we have, so they have got facility by which we can transform all the flip flops into this shift register. So, that can be done, and these ATPG tools they are also there, which take help of these scan based circuits, so that the test pattern generation becomes simple compared to sequential circuit. So, where we have got flip flops, this test pattern generation is a complex problem, but once we have got this scan incorporated into the system, so this entire system can be treated as a combinational circuit only. So, that way the combinational ATPGs can be used for generating the test patterns. So, in design for testability, we have got this another important issue is with the PCBs. So, this is basically in PCB what we have is we have got a number of chips mounted. So, they are mounted in some fashion, and each of these chips. So, if this is the PCB that we have, so on this PCB we can have several such chips mounted. Now, this has got, so if we want that these flip flops they should be initialized to some value. Okay. So, they have got their own scan chains inside, Now, how to take help of those scan chains, and if we want to shift in some serial pattern through this into these scan chains. So, how can it be done? So, this is done by means of this boundary scan structure. So, what happens is that, so one boundary scan cell, so it is structured like this. So, this normal input will come from this on this input line, and this scan input will come on this line, and this shift control will control whether this input will go or this scan input will go. So, accordingly this will come to this capture flip flop. So, this when this capture clock comes, then the pattern gets the response gets captured onto this. So, it can go to the scan out of this cell, so that it can be connected to another scan cell entry. And this also we have got update. So, this update will be updating the output of this cell, and then it is going to this boundary scan cell control, and that can go to this pad. So, this is the input output pin. So, from the input output pin we can have this input output cell, and that connect to the IC, or from it can go to IC, or if it is an output. So, we can see the output at this pad. So, from this pad the value can come to as an input to the IC, or it can go, we can observe the output from this point. So, these are used for this PCB manufacturing, PCB testing and all that. So, there is an IEEE standard which is called test access port, where we have got this line test clock, test mode select line, test data input line, and test data output line. So, any chip that follows this particular TAP standard, this IEEE standard, so they can be connected over a boundary scan architecture. Also, there are built-in self-test structures. So, where what happens is that the circuit under test we do not apply test patterns from outside. So, in the circuit itself we have got a test pattern generator and a response analyzer integrated. So, from outside it just tells that okay, it should start testing now. So, accordingly this test pattern generator, it will go on generating the test patterns, they will be applied to the circuit. The responses that we get, so they will be compressed at this output response analyzer, and then this at the when all the patterns have been applied, this output response analyzer, so it will declare whether this circuit passes the test or fails. So, this is very much useful, because from outside I do not have to apply any test vector. So, there is no question of AT from automated test equipment transferring the patterns and all that. So, that way it is very much useful. So, it can be used at device level, PCB level, system level, or field operation. It is particularly important for field operation, because there I do not have any AT available. So, there it is the circuit itself is generating its test patterns and comparing responses to detect its health. So, we have seen that many new testing challenges have been have come due to the increasing size and complexity of these VLSI devices. Feature size, the transistor size is decreasing. Low power VLSI testing. So, the power reduction is an important factor, because it is normally seen that this test power is much higher compared to normal system of normal operation power. We will see why this thing happens later, but this is one fact. And with this increasing power consumption, the temperature is also increasing significantly. So, that also needs to be considered. So, initially we will be concentrating on this testing techniques, ATPG fault simulation and all these things, and towards the end of the course we will look into these advanced topics like low power testing, temperature hour testing, etc. Thank you.